Alright guys, in this chapter I'm going to talk about magnetism. So let's start by talking about what magnetism is similar to what we're familiar with in electricity. So the first thing that we can say is that in magnetism as well as in electricity we have attractive and repulsive forces. In magnetism we have something that we don't call charges, we call them poles. We have the north seeking pole and the south seeking pole. So, like in electricity, where we have charges that are unlike attracting and like charges repelling, in magnetism we also have like poles repelling and unlike poles attracting. So the north pole of a magnet is going to attract the south pole of another magnet, but the north pole of one magnet will repel the north pole of another magnet. The force, the magnetic force between the poles of magnets depends on the distance. The closer the magnets are, the stronger the force, the further apart, the weaker the force, just like in electricity. Now, how is magnetism different from electricity? Well, the North Pole is not positively charged. When you have a magnet, you cannot assign to the North Pole a positive charge. If you bring a negative charge close to the North Pole of a magnet, there will be no force between them. The South Pole is not negatively charged either. Another difference is that a compass is not going to be affected by charges. When you bring a charged object positively or negatively close to a compass, the compass has no reaction to that. In that sense, magnetism and electricity are different. Another very important big difference between electricity and magnetism is that you can put a charge on any object. You can charge any object, an insulator or a conductor, you can charge it positively, negatively, whereas in magnetism only very few materials can be magnetized. Iron, nickel, cobalt, gadolinium, and some other alloys can be magnetized, but it's a very small number of materials that can be magnetized and therefore made into a magnet. A very, very important difference, very big difference between magnetism and electricity is that so far nobody has measured an isolated magnetic pole. We don't really know why there are no isolated magnetic poles, but that is the case so far. So in fact, if you were to take a magnet that has a north and a south pole as usual, and you cut it in two, you do not end up with an isolated north pole and an isolated south pole. Actually, you end up with two magnets, smaller magnets, each one with a north and a south pole. So isolated magnetic poles have never been discovered. So that's a very important difference with charges, where some objects sometimes can be charged positively or negatively. You can have an electron, which is an isolated negative charge. You have a proton that is an isolated positive charge, but that doesn't exist in magnetism. Now, because of this, because we can never find an isolated north pole or a south pole, we are going to have to define the magnetic field and measure a magnetic field by using a test dipole. If you remember, in electricity, we define the electric field by bringing a test charge, which we assume to be positive, so unimportant. But with magnetism, there's no way to bring a test magnetic pole, to measure a magnetic field. We always have to bring a test dipole, that is a magnet that has a north and a south pole. Despite that, we can still define the direction and the strength of a magnetic field at a given point, because our test dipole is going to react to the magnetic field, and we can measure the net force that is acting on our test dipole, and we can also measure the orientation that the dipole is going to acquire in that magnetic field, and that would give us information about the direction of the magnetic field. Just like in this picture, if we have a magnet north and south, and we bring a compass, another magnet that can spin about an axle, that magnet is going to experience magnetic forces, and those magnetic forces are going to force the compass to be aligned, to acquire certain orientation, And we can use that orientation and the fact that there is a net force acting on the compass to define what's the magnetic field at that location and the strength of it and in what direction it's pointing. So we can always, we're going to use that, a test magnet or a compass to define what's the magnetic field at a particular location in space. So with this, our definition is going to be that we're going to assign the direction of the magnetic field at a particular point in space. We can find it by using a compass, and the compass is going to be oriented in a particular direction, and the direction of the magnetic field is going to be in the direction of the compass and away from the North Pole and pointing, if we're close to the South Pole, then it will be pointing into the South Pole. You can see there in red in this picture different magnetic field vectors at different locations. So the magnetic field vector, we can define it as a vector. It has a magnitude and a direction. We can say that it exists everywhere in space because everywhere in space we can bring a compass and measure what's the magnetic field at that location. And the force, the magnetic force that is exerted by a magnetic field in space on the North Pole of a compass, we're going to define it as being in the same direction as the magnetic field, and the magnetic force due to the magnetic field acting on the South Pole of a compass, we're going to define that direction to be opposite to the direction of the magnetic field at that location. So basically, if you had magnetic field lines in space, like the black arrows that I have here, and you bring a compass or magnet to that location, then the North Pole would experience the magnetic force pointing in the same direction as the magnetic field, and the South Pole would experience a force pointing in the opposite direction of the magnetic field, as you can see in the picture. Now, the concept of magnetic field lines can be defined the same way we define the concept of electric field lines. So the idea is that at every point in space we can measure the magnetic field and assign a vector to it, and if we measure the magnetic field at many different points in space, we can connect those vectors with lines, and we add an arrow here and there on that line to indicate the direction of the magnetic field. So these black lines are now the magnetic field lines, which give you information about the magnetic field produced by a magnet. Now these magnetic field lines, as you can see, coming out of the North Pole and into the South Pole, they look very similar to the electric field lines produced by an electric dipole. For the magnet, the magnetic field lines come out of the north, they loop around and they end into the South Pole. For the electric dipole, the electric fields come out of the positive charge and they end on the negative charge. So very similar. Big difference though is in the middle, because for a magnet, the magnetic field lines inside the magnet go from the South Pole towards the North Pole, whereas in an electric dipole, the electric field lines in the middle of the charges go from positive charge towards negative charge. So that's the only difference. Everything else looks very similar. Now, this is an interesting question. Why are the poles of a magnet called north and south? Well, the answer is because when you make a compass with a needle that is magnetized, one side of the needle, which is a magnet, it's always pointing towards the north. That's why a compass is such a useful instrument. The needle of the compass, one side of the needle, which is the one that we label as north, always points towards the north of the North Pole, the Arctic, on Earth. Now this brings us to an even more interesting point, which is if the North Pole of a compass needle, which is a magnet, always points north, it must be because the Earth is a magnet itself. And the magnetic South Pole of the Earth must be actually in the Arctic, in the North Pole. So the North Pole of the Earth is actually its south magnetic pole, as this picture shows you. So the Arctic is a south magnetic pole and the Antarctic is a north magnetic pole. So that way, when we have a compass with the north and a south pole, the north pole of the compass is going to point in the direction of the magnetic field, which goes towards the geographic north pole, which is the magnetic south pole. Now, a very important connection that exists between electricity and magnetism was discovered at the beginning of the 19th century by a Danish professor during a lecture demonstration in his physics class. And what he discovered was that an electric current, when you have a wire that carries an electric current and you bring a compass near this current, the compass is affected by the current in the wire. Basically, what this is demonstrating is that a current in a wire produces a magnetic field in space, because a compass only reacts to magnetic fields. So during this demonstration, this Danish professor noticed that a compass got deflected every time he turned on the current in a wire. So what this shows us is that currents produce magnetic fields. So this is an important connection between electricity and magnetism. We're going to explore this connection in a later video.